All right, let's dive in. Today, we're going to pull back the curtain on the secret language that's running literally everything digital in your life. Your phone, your computer, you name it. It's called Boolean Algebra, and it's the surprisingly simple logic that makes our incredibly complex world possible.
Have you ever stopped and wondered how a machine actually thinks? How does a traffic light know exactly when to change? Or how does your calculator crunch numbers in an instant? The answer isn't some kind of mysterious artificial intelligence. It's a system built on a ridiculously simple idea.
So, how do they do it? The secret isn't magic, not at all. It's a system that's built on one single fundamental concept. And here it is, every single decision a computer makes, from running a massive video game to just loading this web page, it all boils down to just two choices, on or off. That's it. That simple little switch is the foundation of, well, everything. This simple language of on and off actually has a name, and it's the absolute key to understanding how digital circuits make any decision at all. So let's break down exactly what it is and how it works. It's called Boolean logic. And really, it's just a system where every single piece of information gets represented by one of two values, a 0, which means off or false, and a 1, which means on or true. This simple binary system is basically the alphabet for our entire digital world.
And this right here is where the abstract idea becomes a physical reality. Take a look at that last column, example in a circuit. In a real device, a 0 isn't just a number on a page. It's a literal state of no voltage. And a 1 means, yep, there's actual voltage flowing. This is how true and false become real electrical signals that actually make things happen.
Okay, so if zeros and ones are the letters of this language, what are the words? The things that actually do something, the decision makers. For that, we've got to meet the fundamental building blocks of every digital circuit out there, logic gates. First up, we've got the AND gate. Now the AND gate is, well, it's strict. It will only output a 1, or true, if every single one of its inputs is also a 1. If even one of those inputs is a 0, the output is a 0. No exceptions.
This truth table lays it out perfectly. Just look down that output column, the one labeled X. It's always 0, until you hit that very last row. It's only when input A and input B are both 1 that the output finally flips to a 1. The absolute perfect way to picture this is a circuit with two light switches in a row. For that light to turn on, you have to flip switch A and switch B. One or the other just won't cut it.
Next, we have the OR gate. And the OR gate is much more laid back than the AND gate. It'll happily give you a 1 if input A is a 1, or input B is a 1, or any of its inputs are a 1. It only gives you a 0 if all the inputs are 0.
And the truth table shows you this flexibility. The only time the output is 0 is in that very first row, when both inputs are 0. Every other time, as long as there's at least one 1 coming in, you get a 1 going out.
So think of this one like two light switches wired in parallel. You can flip either switch A or switch B, and the light will turn on. You don't need both, and that flexibility is what makes the OR gate so useful.
And finally, there's the simplest but incredibly important NOT gate. It just does one thing. It flips the input. You give it a 1, it spits out a 0. You give it a 0, it spits out a 1. People also call it an inverter for that exact reason. So now we can start combining these gates to build some seriously complex decision-making circuits. But as they get bigger, they also get slower and more expensive. And this is where the real power of Boolean algebra comes into play. It's not just about building circuits, it's about making them elegant and efficient. Okay, take a look at this expression. To build a circuit for this directly, you'd need an AND gate for the first part, another AND gate for the second part, and then an OR gate to combine the results. That's 3 separate components. But what if there's a better way?
Using the laws of Boolean algebra, we can simplify this thing down. First, as you can see in step 1, we use the distributive law to just factor out the A. Now look what's in the parentheses for step 2, B or not B. I mean, think about it. One of those has to be true, right? B is either on or it's off. So the whole expression in there simplifies to just true, or 1. That gets us to A and 1. And the final identity law in step 3 basically says that if you need A to be true and true to be true, well, you really just need A to be true. The entire complex expression just simplifies all the way down to Y equals A.
So, how many gates does our new super simplified circuit need? The answer is 0. That entire 3-gate mess simplifies down to just a single wire connecting input A straight to the output Y. That is the magic of Boolean algebra. We just went from 3 components to none, saving space, cost, and power on a microchip.
This whole idea of simplification and efficiency leads us to 2 very special gates, NAND and NOR. A NAND gate is simply an AND gate with its output inverted, and a NOR gate is, you guessed it, an OR gate with its output inverted. They're the direct opposites of their basic cousins.
So why are these so special? Well, they're called universal gates, and this is incredible. It means you can build any logic function, an AND, an OR, a NOT, anything, using only NAND gates. Or you could build any function using only NOR gates. Imagine you're manufacturing a chip and you only need to produce one single type of gate. It's wildly efficient. And this is all possible because of a clever trick called De Morgan's theorems, which give you the mathematical recipe for turning ANDs and ORs into their NAND and NOR versions. All right, let's just step back for a second and see how this all comes together. We started with a simple idea, on and off, and we built up an entire system of logic that can be simplified and optimized into something incredibly powerful. And this is the core idea, right here. Every single decision, every calculation, every single pixel that lights up on your screen is just the result of cleverly shuffling around these 2 simple states, 0 and 1, using the rules of logic we just talked about. And that's really the beautiful paradox of computing, isn't it? The immense complexity of a modern smartphone is built from the ground up on this foundation of unbelievably simple, elegant logic. It's a whole universe of information that runs on nothing more than yes or no.
Which leaves us with a really fascinating thought to end on. If our entire digital world was built just by breaking down complexity into a series of simple yes or no questions, what's the next huge problem we can solve just by applying that same pure, simple power of logic?